let us discuss as our remedial class a portion of the definition of the axiometric problems, which we have discussed today to a certain extent. The many problems of practical importance are, say, concerned with the solid of revolution. What is solid of revolution? Which is defined or as the deformed a particular item or particular solids, which are deformed similarly about with respect to an axis of revolution. What is this? The axis, the solids are deformed with respect to the axis of revolution. Means axis, there should be a straight line, which is the axis. About this straight line, we have this is our axis of revolution. Means according to with this straight line, we have a revolution itself. Means revolution means forming a round surface around with the keeping the axis at the central itself, and it is symmetrical because the axis will be at the central part of the circle itself through the central point throughout the center of the revolution, which is thus produced. Thus, by the definition of symmetry, means that 2 points are said to be symmetrical is only then when it is away from a particular line or any other object from object equally. So, 2 points equal at the equal distance from a straight line is said to be symmetrical. So here, all the points on the surface of the revolution is equal to the distance of equal distance from the axis, from the central axis itself. So it is thus called axis of revolution itself. The examples of such solids are, say, circular cylinders, which is circular and has an axis, and full all the points on the surface on its surface, irrespective of the thickness itself, is of equal distance from the centroidal axis itself. This cylinder can be closed in both the end, but still it will have this problem. So it will have this phenomenon, and it can be open at both the ends, so it will have the same phenomenon itself. Now, samples. Let the axis of revolution be z-axis. We have discussed that we will go through the polar coordinate system here. Polar coordinate system in case of this axis symmetrical surface. Polar coordinates can be defined like this. It is all we have so far discussed the rectangular coordinate system or Cartesian coordinate system. But here we say we have to take a force equal to x and y, two coordinate axes in a plane that is on x, along x and y, and they are joining at the origin O. And if we find out a point at a distance r from this origin O, and at a distance, its angle is at a distance theta from the x-axis, which is actually the anti-clockwise direction from the line joining O and R. So the polar coordinates from the points will be equal to r and theta, r comma theta, where distance r is from the origin O, and theta is the anti-clockwise distance from the x-axis itself. Now, here what we'll do, we'll consider the axis of z. Along with the axis r and theta, we'll consider the axis of z even. Along with x and y, we'll consider the axis of z, which is the axis of revolution or the axis of the longitudinal axis of the cylinder itself. The deformation, all the deformation being similar with respect to the z-axis. So it is convenient to use cylindrical coordinates. Convenient to use cylindrical coordinate system itself. Now, deformation being symmetrical with the z-axis, it is convenient. Since the deformation is symmetrical about z-axis, the axis component will not depend on theta. Further, the stress component will not depend on theta itself. Further, tau r theta, which is the shear stress acting on a plane whose normal is r, the radius, and is acting and the acting in the direction of theta, means the circumference of the surface, and theta r z, theta z, theta z r means a shear stress which is acting on the plane whose normal is theta, means the circumference, and z is the direction, means that z is the direction along the length direction along the z axis itself. So in both these cases, it is sure this, as there is no the cylinder is open, so both these stresses along this longitudinal direction, it does not exist along with the sigma z itself. The consequently, the differential equation of the equilibrium can be reduced to a special case. So you don't have to consider about the z itself. Now, let us calculate the differential equation itself. Here, so far attention has been focused on the state of stress at a point. In general, the state of stress is a body varies from point to point, and we have to determine the state of stress at every point or at every desired point in a body. State of stress at every point or at every desired point in a body. The state of equations deals with the condition to be satisfied by the stress components. The stress of equation deals with the condition to be satisfied by the stress component itself. So what is the explanation? The state of stress of a point, the general stress of a body varies from point to point. But we have discussed, we have to know the stress at a point, and the general stress of a body always varies from point to point itself. We have determined the state of stress at every point, at every desired point in a body. We have to determine the state of stress at every point or every desired point which is required by us. State of equation deals with the condition to be satisfied by the stress component. We have to make a set of equation which deals with the condition to be satisfied by the stress component when they vary from point to point itself. This condition will be established when the body is in equilibrium itself. We isolate a small element of the body and derive the equation of equilibrium from its free body diagram. So what we are doing, the condition will be satisfied. We are to make a set of equation with the condition that is satisfied the stress component at which vary point to point. So the stress component. This condition will be established when the body, which all particles is in perfectly equilibrium. So we have to isolate a small element of the body and derive the equation of equilibrium from its free body diagram itself. The forces marked as 1, 2, 3, etc. On the left hand face, that is face number 1, the average stress is the sigma x, tau xy, tau xz. And on the right hand face number 2, so and so. Thus, that's sigma, right hand face. Left hand face, we have only sigma, tau xy, tau z, etc. And right hand face, it will be with the left hand bottom and rear set, we have sigma x, tau xy, tau xz, etc. And the right front and top faces, it will be sigma x plus d sigma x by dx into delta x, delta sigma y, delta tau x by delta x into delta x, and delta tau z plus tau zx by delta x into delta z. This becomes the right hand face is delta x distance away from the left hand face, and following a similar procedure, the stress components on the 6 faces of the elements are as follows: sigma x, tau xy, tau xz, and sigma x plus tau sigma x by sigma x into delta x, tau xy plus del sigma tau xy by del sigma lx into delta z, tau zx plus tau zx by dx delta x. So phase 3, this is phase 1. This is phase, this is inside, the rear side is phase 2. And no, not, this is phase 1, the right side is phase 2. This is the changing this equation itself. Phase 3, the bottom side, sigma y, sigma r, sigma y plus tau xy, sigma yz. Phase 4, in top side, sigma y plus del sigma y by del x into delta x del tau sigma y, sigma x by del y, delta tau x by dx into delta x, tau yz, delta yz by delta x into delta z itself. 6, 5, the rearmost plane, that is sigma x, tau x, zx plus tau zy. Phase 6, the face opposite to the, that is the front face, opposite to the rear face, sigma z plus delta sigma z divided by delta zeta, then delta x, delta x plus tau zx plus delta tau zx by dz into delta z plus delta tau zy by delta x into delta z itself. Let the body force components per unit volume in the xy direction are gamma x, gamma y, gamma z. The body force, we know, we have decided that it is the magnetic force, inertia force, and sometimes the gravitational force itself. These body forces are acting on all type of body, and even in the infinitesimal small body, these forces are active itself. These body forces are divided, have three components. So we have taken two components, three components, x, y, z direction. Like gamma is gamma y, gamma z for the equilibrium in the x direction. So you have to add the x direction. You have to add the forces in x direction 1 by 1, and ultimately plus you have to add gamma x, y, gamma z. Originally divided by delta x, delta y, delta z, and going to the limit. Doing the limit, we get delta sigma x by dx, delta tau x by dy, and delta tau 0 is dx by delta z, delta x itself. Similarly, the equation for forces of the z and y and z directions effectively is 0. We have supposed to get two more equations on the basis of that the cross sections are equal. It's tau yx is equal to tau zx, xy, etc., tau zx, tau xy, etc. We have this differential equation, delta sigma x by dx, delta tau xy by delta y, delta tau zx is equal to z itself. Delta x z divided by del z plus gamma x, and sigma y divided by delta sigma, and delta tau xy by del x is equal to tau sigma tau yx divided by dx plus gamma by y equal to 0 itself. So sigma d sigma z by dz is equal to plus delta tau z by dx plus delta yz by delta is equal to gamma z itself. This equation must satisfy at this equation must satisfy at all points throughout the volume of the body. It must be related at the moment equilibrium condition established with the equality of stress. If there exists a plane state of stress, that is, if for a given state of stress there exists coordinate O, X, Y, Z such that for this system, the sigma z is equal to 0, sigma x z is equal to 0, sigma y z is equal to 0, or anything, any stress along the z direction, the tensile, shear are all 0 itself. The stress of stress is said to be a state of plane stress, and two-dimensional state of stress or two-dimensional state of stress in the xy direction plane, then xz is equal to xz equal to tau zx tau zy, tau and yz is all equal to 0. Only sigma x, sigma y, tau xy, gamma x, gamma y exists. The differential equations are that become sigma x, sigma y, tau xy, nx equal to 0, tau y, tau yx equal to 0, and they are to 0 itself. The sequential boundary condition. The equation must be satisfied throughout the volume of the body itself. When the status value over the plane, that is the body having the plane stress, having the plane stress state, the stress of stress component sigma x, sigma y, tau xy must be consistent with that externally applied force at a boundary point. So what is going on here? Say we have a body like this, which is in a plane, not a cubical like this. We have only one 0x, ox and y, and on the point fx, fy, and p to the power n. And tau xy, sigma x, and fy, fx and fy. This is the body force, fx into fy, and it is actually towards the normal itself. Consider the two-dimensional body shown in the figure A itself. At a boundary point P, the outer drawn normal to the end, say fx and fy be the components of the surface force per unit area of this point. Fx and fy must be continuous of this process at the surface. So using the Cauchy's equation, Tx says fx sigma x nx, qxy and y, fy and y, tau xy and x means where nx and ny are direction cosines to the x direction and y direction respectively. If the boundary of the plate happens to be parallel to the x-axis at any point P, the boundary condition become fx is equal to sigma x and fy is equal to tau xy. Okay, let us stop our sharing remedial classes here.